Welcome to this short presentation on radiotherapy. My name's Martin Christlieb. I work for the University of Oxford and in the Department of Oncology. So I work for the bit of the University of Oxford that's responsible for doing cancer research. We have, like most people, we have specialisms, places where we're better at it than, places where we focus our efforts. And one of the places where we focus our efforts is on radiotherapy, on the development of the physics and application of X-rays and other forms of radiation to curing cancer. And that's what we're going to have a look at today. Radiotherapy's been around for a while, so the first recorded uses of radiation against cancer are 1896 with Emil Grube's work. But radiotherapy is allowed to blossom by the discovery and the development throughout the 20th century of linear accelerators, the machines that generate X-rays for use in radiotherapy. And I suspect you don't need me to tell you that this picture is of a machine that was developed and built in the 1960s. It's a pretty 60s looking object. And this is an up-to-date one. This is a modern, 21st century linear accelerator. This is the machine that will deliver a burst of X-rays to try and kill a tumor inside a patient. Radiotherapy is an absolute workhorse of cancer medicine. So by one estimate, radiotherapy is responsible for something like 40% of the success we do have. So when we are able to successfully treat patients, radiotherapy is a big part of that. And we use it to cure, to relieve symptoms, to shrink tumors and clean up small deposits. So I thought we'd have a look at today, how does radiation work? What's the basics of radiation? How does it work? What are the challenges? What have we been able to overcome? And why are departments like ours still doing physics-based research to improve radiotherapy, and what might come next, and what are the challenges we've got to overcome? And so what we're going to have a look at first is just a little bit of basic radiation physics so that we can understand how it works and what we're doing with it. So the first question is about radiation and what is it? And for many of us, I guess we experience we come across radiation at school. We're taught about alpha particles and beta particles and gamma rays. And when we're taught that material, we're very much taught that material in terms of radioactive stuff. So you've got a bit of uranium, a bit of plutonium, and that's throwing out radiation. So the radiation's coming from the atoms. And it can throw out alpha particles or beta particles or gamma rays. But actually, from the point of view of something like radiotherapy, radiation is really just packaged traveling energy. I want to take a bundle of energy, I want to package it up in a form that will travel, and I want to be able to aim and deliver that radiation to a point in space, or to a point in a patient, and then have that energy delivered so that it can cause the damage that will kill the cancer. And so from that point of view, actually, that cannon is shooting out a piece of radiation. That cannonball represents a packaged lump of energy. I'm going to take a bunch of gunpowder, which is not much good to me. I'm going to shove it in the cannon. I'm going to roll the ball down on top. I'm going to set fire to it, and the gunpowder is going to explode. All that energy is going to be packaged up in the cannonball. The barrel of the gun allows the cannonball to be directed. The ball will fly across a field, carrying the energy with it until it smacks into the side of the castle wall. Bit's going to drop off the castle wall. Success, we've done the damage we set out to do. So in that sense, it's traveling energy that I'm interested in. Well, that's interesting, but we're not talking about cannonballs, we're not talking about castles, we're talking about people. So you might be quite keen to know that I'm able to understand how much energy we're going to use. When we prescribe drugs, we don't just tell you to take some. We prescribe 300 milligrams once a day. So here I want to prescribe so much radiation once a day. And in this case, we don't care how much radiation leaves the cannon so much as we care about how much radiation reaches the castle wall. I care about how much energy is deposited in the target. And the way to do this was set out by a guy called Hal Gray. He was a UK physicist funded by the Medical Research Council, and he developed the idea that what we care about is the amount of energy, the joules of energy, deposited in a bit of matter, which we might call a kilogram. So joules of energy in a kilogram of matter. That's the fundamental unit. Everybody agreed with him, so they called the unit Gray after him. So when we give radiotherapy, what we're going to do is we're going to prescribe so many Gray of radiation. And the standard course of radiotherapy might be something like 60 to 70 Gray of radiation. That turns out to be quite a lot. So we usually give that in maybe 2 Gray fractions. So you might turn up at a hospital once a day and take your pill of radiation, your prescribed dose, your 2 Gray fraction. Now, I don't know about you, but I find the idea of a Gray quite a difficult thing to wrap my head around. And I don't know what a joule is, and I barely know what a kilogram of matter looks like. I guess it's 2 small bottles of water. So a little bit of a thought experiment. What happens if I drop a 2 Gray radiation dose into a can of drink? So that's about 330 mils of water in that can. What happens if I drop 2 Gray of radiation into it? That's the standard sort of daily dose. Well, it turns out that a 2 Gray dose to a can of drink raises the temperature of the can of drink by about 0.5 millicelsius. So I would need to put over 1,000 Gray of radiation into a can of drink to raise the temperature by 0.5 degree Celsius. So this is really, really tiny doses of radiation. We're a long way from a cannonball flying across a field here. There is not a lot of energy going in. So if it's not a lot of energy, how can it do that thing we want it to do? How can it damage a tumor? How can we get this tiny cannonball to make an impact? And the answer is that the castle wall we're aiming at, the thing we're trying to damage, is quite small in itself. And this tiny little packet of energy is perfect for knocking bits off a cell's DNA. Now, every cell in your body has an amazing capacity to repair DNA, but cancer cells are a bit weird. Cancer cells are mutated, and often those mutations damage a cancer cell's ability to repair DNA. Also, cancer cells are quite busy, so they've got a lot of work to do, and it's easy to overwhelm, or relatively easy to overwhelm, their ability to deal with and repair this damage. And if a cell has damaged DNA, the cell will die if it can't fix it. Normal cells are able to be reasonably robust. Cancer cells are a little bit vulnerable. So these little packets, these cannonballs, are trying to knock holes in DNA. There's a number of ways of delivering these cannonballs. We can deliver them by putting tiny little seeds of radiation into a tumor. We can deliver radioactive drugs, but the workhorse of cancer therapy is external beam radiotherapy. So we're going to have a patient here, and this machine is able to deliver a stream of X-rays, a stream of these little light particle cannonballs to the patient's tumor and knock bits out of the DNA. And that's what we're going to talk about today. So let's have a look at X-ray beam, external X-ray beam radiotherapy. And let's go back to the idea of this cannonball aimed at a castle wall, because we have got a little bit of a problem. When we fire a cannon at a castle wall, the cannon dumps a bunch of energy into the cannonball starts flying. The cannonball flies across the field, and eventually the cannonball will hit the castle wall. All the energy will be deposited into the outside brick or the block of the castle wall, and that brick will be damaged and fall off the castle wall, and we've left with a hole, which is kind of what we wanted to do. So if we keep firing that cannon, this hole's going to get bigger and bigger until the whole wall falls down, and we can send in the troops to take the castle. Unfortunately, weird stuff happens when you get really tiny. The photons, the X-ray bits, the little packets of energy that come out of an X-ray gun are so small that they're entitled to behave a bit weirdly. So if we fire this gun, out comes a little packet of energy. The packet of energy flies through the air towards the patient. But instead of hitting and knocking bits out of the first brick it encounters, it can knock energy out of maybe the third brick it encounters. And that will damage that space. It could do that, or it could knock out of the fourth brick, or even the last brick, which sets us a really interesting physics challenge. How can we predict where each photon, where each little packet of energy, each little tiny cannonball, where is it going to do the damage? Because if I'm trying to treat somebody, I really want to know where that damage is going to happen. I cannot have it just going anywhere. And that's a real challenge, because actually we cannot predict where a single photon will go, where a single one of these cannonballs. We have no idea. But we can play quite an interesting game if we think about how you'd play roulette. If you play roulette, you spin this wheel, you throw a ball in and set it going round. The ball eventually bounces around and lands on a number. You've no idea where that's going to go, obviously, because otherwise you'd be immensely rich. So we don't know where the ball's going to go, but actually we do know that there's a 1 in 37 chance that it will go on the red 3. There are 36 coloured numbers and a green 0, so 37 possibilities. I still don't know where a ball's going to go, so each ball is going in a random place, and I don't know where each ball's going to go, but I do know there's a 1 in 37 chance of it going to each number. And you might be sitting there thinking, well, you keep saying 1 in 37, but that doesn't help me, because I really want to know where the ball's going to go, right? Because I really want to know where I'm staking my house or my car. Well, I can't help you with that, but if you had 37 million houses to stake, 37 million $100 bills, you would know where the ball was going to go. Because if you roll the wheel 37 million times, you know that more or less, each one of these numbers is going to be hit 1 million times. And of course the casino does know that, and the casino plays the game like that, and that's why the casino wins, because the casino can afford to roll the wheel 1 million times. You can't. But I could program a computer to understand not where one photon, where one little cannonball will go, but I can ask it where 2 or 3 billion cannonballs will go. And that, just like rolling this wheel 37 million times, I can get a pattern of where all those little cannonballs will go. So let's fire this gun. Let's do this experiment. This is what we would do in reality. We get a computer to simulate, to roll the wheel several million times. And the analogy with roulette is so close that this is called Monte Carlo modeling. So the first little cannonball flies out of here, damages this brick. The second one damages this one. Third one damages that one. The fourth one goes here. The fifth one goes here again. So now we've got 2 strikes in this area and there. So you can see over time we don't know where each photon will go, but a pattern is emerging. There's not a lot of damage happening here. There's a bit of damage happening here. So by rolling the wheel, by playing this Monte Carlo game billions of times, the computer is able not to tell us where a cannonball will go, but it is able to tell us the pattern of damage. It is able to predict what will happen. And that's really important. Those of you with slightly skeptical minds might tell me at this point that we still have a problem. Most of the damage is being done here. But what if my tumor's here? Well, that is a real problem. There's nothing we can do about this. If we roll the dice, if we spin the wheel millions and millions of times, if we look at what happens, we find that this is a real simulation of what happens if you throw these little X-ray cannonballs into a human being, into water, in fact. So this is about 0 to 16 centimeters worth of person. And you can see that early on, just inside this bit of water, just inside the patient, I'm getting a little bit of damage which builds up to a maximum at about 1.5 centimeters. So that red block that was being damaged, most of that damage is being left at about 1.5 centimeters. And then the total damage kind of tails off until you're out of the other side of a person. So it's about, 16 centimeters? If you imagine this graph going out to about 25 centimeters, that is about the width of me. But my tumor might be here. I don't want to do that, because that's going to cause loads of damage somewhere where I don't want it, and not enough damage somewhere where I do want it. And so what we need to do, we need to ask a bunch of physicists to get a decent computer to solve this problem for us. How do I make something that's going to do damage here actually focus where it doesn't want to focus, but I do want it to focus? And to do this, and to illustrate this problem, I'm going to introduce you to a patient that I think you might recognize. This is my computer mouse from my desk at work. So here we've got an X-ray scan of the mouse. You can see there's one of the buttons here. There's the other button. There's the wheel in the middle that you would use to scroll. There's the cable. I haven't yet progressed to Wi-Fi mouses. or mice even, I suppose. And this is and so what we're going to do is we're going to pretend that this little semicircle here is a tumor. And I'm going to ask the computer to simulate what happens if I shine billions of photons. We're going to do this Monte Carlo modeling and ask what happens if I send a beam in there to knock out that tumor. So here's a beam, it's coming from the top. Just as we saw with the simulation, most of the damage is done early on, and that damage fades away until the beam leaves the patient. And there you can see that little half circle tumor. It's getting a decent dose. We'd like it to be a bit more. That's not a bad dose. That would be acceptable, I guess. But look at this damage to the bits of the mouse that aren't within the tumor. That's damage that will hurt somebody. That's damage that will leave side effects. So this is not a good plan. Let's not do that. There's nothing we can do about the pattern of damage, but we can play some really clever games if we use more than one beam. Let's introduce a second beam from the bottom. Two things to remember here. One, the beams are not uniform. Remember, most of the damage is done right at the start. So most of the damage from this beam is done at the start here. Most of the damage of this beam is done at the start here. The two beams travel through the same bit of the mouse, but the two beams are not the same intensity. The number of cannonballs being fired per second is different. So this beam is much more intense than this beam. It's still not great. We've still got a lot of damage here, and that's not where the tumor is. But look how much less damage is being done there than in the previous slide. Go back. Compare that to that. This is still not good. I mean, we don't want to do this, but it's a huge step forwards. But of course, we don't have to settle for two. We could introduce a third beam. Look at the impact of that beam. We still have a hot spot here. There's still damage being done here that I'd rather not do, but it's a faint yellow type of, it's a very much lower faint yellow color. But look at the tumor. The tumor's now being coated in this lovely orangey yellow color. That's probably enough to kill the tumor, but we're now going to do way less damage to the patient. Okay, well, let's change the orientation of the beams. You can see things get a little better still. Lost the yellow color from here. This blue color is pretty good. Your body's not bad at dealing with that amount of radiation. Still getting a good level of radiation into the tumor. Okay, so why settle for 3? Let's try 5. Maybe we've gone too far here. We've introduced a hot spot here now, which I don't really want to do. But let's simulate 7 and see what happens. So we can see here, this now begins to look like a really good plan. The second 3-beam plan looked pretty good. This plan looks pretty good. We've got a little bit of a hot spot here, but it's not too serious, and a really nice dose of radiation to the tumor. So by using multiple beams, the physicists are able to overcome that problem that the peak dose from any one particular direction is not in the right place. By catching the tumor in the crossfire, the tumor's taking the brunt of all 7 beams. The rest of the tissue's only got to deal with 1. Remember, healthy tissue, pretty good at dealing with small doses of radiation. Tumors often got mutations and a busy lifestyle that means it's much less able to cope. So this should give a good result. Those of you who have sharp memories will remember that I described the tumor as the semicircle. I didn't describe that circle as part of the tumor. That circle is potentially a healthy thing, a healthy organ that I don't want to damage. And using an X-ray beam, I'm really struggling to pull that little circle out of the radiation field. Is there a trick we can play that saves that little circle? Well, there might be. But it means buying some new kit, and it means investing in a slightly different type of cannon and a slightly different set of cannonballs. It means moving away from X-rays and using a proton beam. So remember, when we had X-rays, we were firing these little tiny packets, these little tiny cannonballs, hitting the castle wall, the patient, and the cannonballs were landing a bit randomly, but if we simulated enough cannonballs, we got this pattern, and we had a bit of a problem because the major damage is not necessarily where the tumor is. But there's nothing we can do about that. That's the physics of an X-ray photon. If you look at what happens to a proton, something very different. You get much more consistent cannonball-like behavior. The balls still travel into the patient before they drop their energy, so it's still the slightly weird physics of the small, But now we're seeing a pattern where there's a little bit of damage, a little bit of damage, a little bit of damage, a big spike of damage, and then nothing beyond. That's because these protons are flying in, doing damage as they travel, and then stopping travel. And that's really exciting, because if we go back to our patient and look at the way a computer simulation deals with the dose that would result from a proton beam, you can see now that I can still dump a good dose of energy into the tumor, but we can see this organ is starting to be spared. Of course, there's no reason to stop with just a proton beam. We can try multiple beams. And by refining the solution, the physicists can get us down to this situation. We've got really quite good doses in the tumor, a little bit of high dose just outside it, but now for the first time we're seeing reasonable sparing of this circular organ. We're seeing some sparing of the lead that comes out to the computer. This is a really nice solution. So you might be sitting there thinking, well, why on earth are we not just buying these things and using them? And the answer to that is kind of twofold. One is the slightly boring answer, which is that these machines are really expensive. They are something like 100 times more expensive than the X-ray kits that we have even in a modern 21st century hospital. The second answer is a little bit more interesting, and it explains why departments like oncology, like the Oxford Institute for Radiation Oncology that does this work, still need to do a bit of work, still need to make sure that we're on top of our game, because there is a little bit of a problem with this. And the problem comes that because the beam stops, we must know where the edge of the tumor is. So here's my beam, here's my cannon, it's firing these little protons into the patient. And if I've adjusted the beam so that the protons stop in this square here, that's where most of the energy will be deposited, that's where most of the damage will be done. If that is the tumor, then we are in a happy day. But if the beam stops short, then the tumor will be spared any radiation at all, and I'll do some damage to healthy tissue. If the beam goes too far, I'm going to spare the tumor the worst impact, which I don't want to do, and cause some damage to somewhere where I don't want to damage. So I need to get it right. I need to image, and my imaging, my understanding of where the tumor is really has to be spot on, and it has to be spot on for each and every patient, every time. And of course, people move. And they move as they breathe. So any tumor that's within the main cavity of the body is potentially moving as the patient breathes. And so one of the challenges that people like the Oxford Institute for Radiation Oncology, the Department of Oncology, are one of the big challenges that we're working on is can we make this technology perform despite this sort of challenge? If the NHS if health providers are going to buy this technology, then we have to make sure that it works as hard as it can possibly work and delivers the clinical benefit that it ought to deliver. The physics here is epically cool, but people move, and we need to be robust to that, and that's the challenge that my colleagues are working on in Oxford. So hopefully we've seen a little bit about how radiation physics works. We've seen how we are trying to package energy, drop energy into malignant cells, into tumor cells, into a tumor, and damage it. And we've seen that with X-ray photons, the challenge we face is that of crossing beams to catch the tumor in the crossfire, to shape the radiation dose around the tumor so that the tumor gets damaged and the patient doesn't. And that's been very successful, this multi-beam approach used in hospitals, and the side effects are very much lower than they would have been 20 years ago. Protons are really exciting new technology, but it's expensive, and it has to deliver to make that expense worthwhile. And one of the challenges that it faces, and the people like us are working on, is how can we deliver that benefit to large numbers of patients and be robust to things like patient movement. So thank you very much for watching, and I look forward to talking to you again some other time.